Hello, dear students. This is Dr. Sourav sir's class. This is our this question is came from the 2023 National Boards of Higher Mathematics PhD entrance test. This question is about linear algebra. We can see that. So the question tells us to find the true or false. So the given statement is suppose A be a n cross n complex matrix. So A belongs to our M N C. Okay. Now for all n, now for some n greater than equals to 2. The point to be noted for some n greater than equals to 2. Okay. So with the property that every matrix that commutes with A is a polynomial in A. Okay. So our option A is such a matrix A is necessarily diagonalizable. Our point B is such a matrix A cannot be nilpotent. And option C is the characteristic and the minimal polynomials coincide for every such A. So let us take something. Take the matrix. A will be my this 0, 1, 0, 0. And our B can be what? B can be okay. I want to take this. Okay. So where our AB belongs to R. AB be any natural number. Okay. So we can write this thing. We can write our B as B of A plus AI. So that is now a polynomial, no? That is a polynomial. This is my scalar, this is my scalar, and this thing, these two things are vectors. So this thing is kind of polynomial in A. So our option A. Okay, now we have to check those things. Now our A is nilpotent because all the eigenvalues are 0. We can see that our A is nilpotent. Otherwise we can do another thing, that our A square is equals to what? Our A square is equals to, yeah, so this is my 0, 0 and 0 and 0. Okay, so our A square is equals to 0, so our A square is nilpotent. And another thing we can say that on the other way, our if the 0 is the only eigenvalue of the matrix, so that matrix will be nilpotent. So our A is nilpotent, and A is not diagonalizable because our A is on a Jordan block that says that our 0 is sharing single eigenvector. We can do that easily. And our 0 is sharing single eigenvector. So the geometric multiplicity of 0 is my 1 and algebraic multiplicity is 2, so that is not diagonalizable. So my A is nilpotent and it is not diagonalizable. So our option A is false and option B is also false. With the same example, we can see that our option B is false and option A is false. Option A told us that the matrix will be necessarily diagonalizable. We can easily see that this is not diagonalizable, and our option B says that A cannot be nilpotent, but our A is nilpotent, and that is satisfying all the conditions. Okay, now we are moving forward to our option C. Option C says us what? That the characteristic and minimal polynomials coincide for every such A. I think this is true, but we are gonna prove it. Now, a matrix A. Let me change my font color. Yeah, let a matrix A has equal characteristic and minimal polynomials CHA and MA. If and only If and only for what case? Then, yeah, firstly I want to write this thing. If and only if, or for each of its eigenvalue, for each of its eigenvalue, A has one Jordan law. And another thing is I have to say in addition with it. So in additional with it, so our and if and only if every matrix that commutes with A is a polynomial in A. So what have I written? We know that the characteristic polynomial and minimal polynomial is my same. If and only if condition is what? So for each of its eigenvalue, A has one Jordan law, and if and only and the second if and only if condition says that every matrix that commutes with A is a polynomial in A. So that thing is given in our. Oh, they told us the sufficient condition only. Yeah, so this is my true. So our option C is true. I'm gonna write it that our option C is the only true statement and our A and B are false. So our C is the correct answer. Hope you understood. Thank you guys.